In this lecture, we'll define quasi-geodesics. Quasi-geodesics are quasi-isometric embeddings of a geodesic. We'll prove that in a hyperbolic metric space, geodesics and quasi-geodesics joining same pair of points lie in a uniformly bounded neighborhood of each other. So this property is called stability of quasi-geodesic. And using stability of quasi-geodesic, we'll prove that if there exists a quasi-isometry between two metric spaces, x1 and x2, suppose x1 is a hyperbolic metric space, then x2 will be also a hyperbolic metric space. So let us begin with the definition of quasi-geodesic. Let us start with a metric space X, and let us take lambda to be greater than equals to 1 and epsilon to be greater than equals to 0. A map from this closed interval AB to X is said to be lambda epsilon quasi-geodesic if alpha is lambda epsilon quasi-isometric embedding. So by this, what do we mean? So 1 by lambda times mod of s minus t minus epsilon is less than equals to distance between alpha s and alpha t less than equals to lambda times mod of s minus t plus epsilon for all st belonging to this closed interval AB. So this is the meaning of quasi-isometric embedding. For example, if I take this map alpha from this closed interval 0, 10 to R, so you can take any Rn also here. So alpha x is defined to be this box x, which is the greatest integer function for this x. So alpha x is this box x. So image of alpha, it is just integers. So alpha x is box s. Alpha, so this is a quasi-geodesic. So this is very easy to see. So note that this alpha, it is not a continuous map, but it is a quasi-geodesic. So therefore, so this quasi-geodesic, it need not be continuous map. And also note that in this above definition, if I take lambda equals to 1 and epsilon equals to 0, so you get the definition of geodesic. Okay. So this quasi-geodesic, it need not be continuous. But so what we can show, so for any quasi-geodesic alpha, there exists a continuous quasi-geodesic beta joining the endpoints of alpha such that beta and alpha lie in a uniformly bounded neighborhood of each other. Yeah, so that is the thing I have written in this proposition. So let us take alpha to be a lambda epsilon quasi-geodesic defined on this closed interval AB. So there exists lambda prime epsilon prime greater than equals to 0 and k greater than equals to 0 and a continuous path beta defined on this closed interval AB such that beta is lambda prime epsilon quasi-geodesic. Endpoints of beta are same as the endpoints of alpha, and this alpha it lies in k neighborhood of beta, and beta also lies in k neighborhood of this alpha. So this lambda prime, epsilon prime, and k, so this depends only on this lambda and epsilon. Okay. So how to prove this? So let us take a partition of this closed interval AB in this following way. So this T0, T1, Tn, so this is a partition of this closed interval AB such that mod of Ti minus 1 is equal to 1, and Tn minus 1, it is less than 1. Now, so this distance between alpha Ti and alpha Ti minus 1, so this will be less than equals to lambda times this Ti minus Ti minus 1 plus epsilon. So this is because this alpha is lambda epsilon quasi-geodesic. Again, so this mod of this Ti minus 1, so this is less than equals to 1. So therefore, distance between alpha Ti and alpha Ti minus 1 is less than equals to lambda plus epsilon. Now, let us take a geodesic in X joining this alpha Ti and alpha Ti minus 1 and alpha Ti. So Ci, it is a geodesic joining alpha Ti minus 1 and alpha Ti. And let Fi defined from this closed interval Ti minus 1 to Ti to this closed interval 0 to distance between alpha Ti minus 1 and alpha Ti be a linear reparameterization of this closed interval such that Fi of Ti minus 1 is equal to 0 and f of Ti is equal to the distance between alpha Ti minus 1 and alpha Ti. So this always you can do. And let us now take beta I to be equal to Ci compose Fi. So now this beta I, it is defined on this closed interval Ti minus 1 comma Ti to X. So note that this image of this beta I is same as the image of this Ci. So this beta I, it represents the geodesic Ci. So let us draw a picture. So we have taken this alpha to be a quasi-geodesic. So it may not be, so the image of this alpha, it may not be continuous. It is something like this. And now what is my this new path beta? So what I have done here, so I have taken a partition, something like this. So suppose this is my alpha Ti minus 1 and this is my alpha Ti. So now what I have done, so I have joined this 2 points by geodesic. So this all these blue paths are geodesics. And now what you do, so you take the concatenation of this beta I to get the path beta. So that will be a continuous path. So the claim is that the continuous path, it is again, it is a quasi-geodesic and it lie in a k neighborhood of this alpha, and this k depends only upon this lambda epsilon. Okay, so here we have defined this beta t. So beta t is defined to be beta it if this t belongs to this closed interval ti minus 1 ti. So therefore beta is the concatenation of this path beta I. So let me go back to this picture again. So this path is beta I, this one. Okay. So now what we want to prove that this beta it is a quasi-geodesic. So let us take 2 points to t and t prime in this closed interval AB. So there will exist points ti and tj such that mod of t minus ti is less than equals to 1 and mod of t prime minus tj is less than equals to 1. And also we assume that t is less than equals to ti is less than equals to tj less than equals to t prime. So then distance between beta ti and beta t, so this will be less than equals to lambda plus epsilon, and distance between beta t prime and beta tj, so this will be less than equals to lambda plus epsilon. So now what is the distance between beta and beta t prime? So you apply this triangle inequality. So this will be less than equals to distance between beta ti, beta tj plus twice of this lambda plus epsilon. And now note that this beta ti is same as alpha ti, beta tj is same as alpha tj. Now you know that this alpha, so this is a quasi-geodesic, lambda epsilon quasi-geodesic. So you apply this thing here, so you'll get this inequality. It is less than equals to lambda times mod of ti minus tj plus epsilon plus 2 times lambda plus epsilon. So this will be again less than, because t is less than equals to ti is less than equals to tj is less than equals to t prime. So this mod of this will be less than equals to mod of t minus t prime. So therefore this will be less than equals to lambda times mod of t minus t prime plus epsilon plus twice lambda plus epsilon. Also note that, so distance between beta ti and beta tj, which is exactly equal to the distance between alpha ti and alpha tj. Alpha is again, it is a lambda epsilon quasi-geodesic. So this will be greater than equals to 1 by times 1 by lambda times mod of ti minus tj minus epsilon. And also mod of t minus t prime is less than equals to mod of ti minus tj plus 2. So therefore distance between beta t and beta t prime, it will be less than equals to 1 by lambda times mod of t minus t prime minus 2 minus epsilon minus twice of lambda plus epsilon. So therefore from this above two inequalities, this one and this one, so this beta it will be a quasi-geodesic. And also note that, so if I take any t, so distance between alpha t and beta t, so this will be less than equals to twice lambda plus epsilon. So therefore this beta and alpha, so they lie in a k neighborhood of each other, where k is equal to twice 2 times lambda plus epsilon. Okay, so we have proved this proposition. So now given a quasi-geodesic, so without loss of certainty, I can take that quasi-geodesic to be a continuous path because of this proposition. Okay, so now let us move to the statement of the stability of quasi-geodesics. So let us start with a non-negative number delta, lambda to be greater than equals to 1 and epsilon to be greater than equals to 0. So then there exists a number r depending only on this delta, lambda, epsilon such that the following holds. So if X is a delta hyperbolic metric space and alpha is a quasi-geodesic, alpha is a lambda epsilon quasi-geodesic in X, and beta be a geodesic joining the endpoints of this alpha. So then alpha lie in a R neighborhood of beta and beta lie in a R neighborhood of this alpha. Okay. So without loss of generality by this previous proposition, we can assume this alpha to be a continuous lambda epsilon quasi-geodesic. So let us take this P to be alpha A and Q to be alpha B. And let us denote this geodesic beta to be like this. Okay. So now what we do, so alpha it is a, now it is a continuous path, which is a quasi-geodesic. Take D to be the supremum of the distance of X to alpha. So where, so this X, it lies on the geodesic joining this PQ. So now because this alpha it is a continuous path, so there exists X naught belonging to this geodesic such that the supremum D is attained at this point X naught. So now what you do, so consider the open ball around X naught of radius D. So first of all, note that because you have taken this D to be the supremum, so this open ball, it does not intersect alpha. So we have a picture here. So this is my beta and this one is my alpha. And this ball, it does not intersect alpha. Okay. So now let us take a point y on the geodesic joining px naught such that the distance between yx naught is equal to 2d. So let us take a point y in this part such that the distance of y to x naught is 2d. If that point is, if we do not get that point, so if distance between x naught and p is less than 2d, so then we'll take this p to be just y, equal to y. Similarly, in the other direction, so let z belongs to the geodesic joining x naught and q such that the distance between z and x naught equal to 2d. And again, if distance between x naught and q is less than 2d, so we'll take this z to be equal to q. So we have a picture something like this. So here is my y and here is my z, which is lying outside this open ball, and this distance is 2d, this distance is 2d. And if the distance between p and x naught is less than 2d, we will take y to be equal to p. Similarly for the other part. Okay. So now, so this distance between y and alpha, so this will be less than equals to d because d is the supremum. And distance between z and alpha, so this will be less than equals to d. So therefore, there exist points y prime, z prime in alpha such that distance between y and y prime is less than equals to d and distance between z and z prime is less than equals to d. So again, let us go back to this picture. So for this y, we have this y prime which is less than equals to d, and for this z, we have this z prime which is less than equals to D. Now consider the path gamma to be the geodesic joining y and y prime, union the part of this alpha joining this y prime and z prime, union the geodesic joining y prime and z prime. So here we are taking this path. So that is this path gamma. So this path is gamma. Okay. So now note from the proof of this exponential divergence of geodesics. So the way we have proved this exponential divergence of geodesic, so we can show that the distance between x naught to alpha is less than equals to delta times log base 2 of length of gamma plus 1. So this you try to prove with the help of this exponential divergence of geodesics. So once you prove this thing, so length of gamma, so this will be less than equals to 2d plus lambda 6d plus epsilon. So why this is true? So this gamma, it is union of this two geodesics and this quasi geodesic restricted to this y prime and z prime. So alpha is lambda epsilon quasi geodesic. So length of this alpha, so this will be less than equals to lambda times distance between y prime z prime plus epsilon. So therefore this length of gamma, so this will be less than equals to 2d plus lambda times 6d plus epsilon. Yeah, so distance between y prime and z prime by your construction, so this will be less than equals to 6d. So from this, it will follow that this length of gamma, so is less than equals to 2d plus lambda times 6d plus epsilon. Also note that, so this ball of radius d around x naught does not intersect alpha. So the distance between x naught and alpha, so this will be greater than d minus 1. And also we have observed that this distance between x naught and alpha is less than equals to delta log base 2 length of gamma plus 1. So therefore d minus 1 is less than delta times log base 2 2d plus 6 lambda d plus epsilon plus 1. And so therefore what we get, 2 to the power d minus 2 by delta is less than 6 lambda d plus 2d plus epsilon. The left hand side, it is exponential function of d, and the right hand side, it is linear function of d. So this d has to be bounded. So d has an upper bound, say d naught. And we have taken this d to be the supremum of distance between x to alpha, where x belongs to this geodesic joining P and Q. And so d is less than equals to d naught. So therefore, so what we have proved that, so this geodesic joining P and Q will, so this geodesic joining P and Q will lie in d naught neighborhood of this alpha. So now the other part, it is easy. So you do not require hyperbolicity in the other part. So let this closed interval a prime b prime with the maximal subinterval such that alpha restricted to this interval lie outside D neighborhood of this geodesic joining PQ. Now you apply the connectedness argument. So by connectedness, there exists a point W in this geodesic joining PQ and a point T belonging to this closed interval A prime and T prime belonging to this closed interval B prime B such that distance between W and alpha T is less than equals to D naught. Distance between W and alpha T prime is less than equals to D naught. So this will imply that distance between alpha T and alpha T prime, so this will be less than equals to 2D naught. And we know this alpha, it is a quasi-geodesic. So distance between alpha T and alpha T prime, it is greater than equals to 1 by lambda times mod of T minus T prime minus epsilon. So this thing is less than equals to twice of D naught. So this will imply that mod of A prime minus B prime, which is less than equals to mod of T minus T prime, will be less than equals to 2 lambda T naught plus lambda epsilon. So if you draw a picture of it, it will be clear. So I leave it to you to check this thing. So therefore, length of this alpha restricted to this interval A prime B prime is bounded because the length of this interval A prime B prime that we have proved to be bounded, and the bound depends only on this lambda epsilon and D naught. So D naught again, it depends on this lambda epsilon and delta. So therefore, we have proved that this length is bounded, length of alpha is bounded. And now let us take this D1 to be twice lambda D naught plus lambda epsilon. So this alpha, it will lie in D1 neighborhood of this geodesic joining, this PQ. And if I take this R to be maximum of this D naught and D1, so we have the required result. Now as a corollary, so we'll prove that this hyperbolicity is quasi-isometry invariant. So let us take a K epsilon quasi-isometry between these two metric spaces X and Y. And we will also take this X and Y to be geodesic metric spaces. So if X is delta hyperbolic metric space, so then there exists delta prime depending on this K epsilon delta such that this Y is delta prime hyperbolic metric space. So now, first of all, note that for each element Y in the codomain space, so there exists an element X suffix Y in the domain space X such that distance between Y and phi xy is less than equals to K. Now consider the map psi from Y to X. So psi of Y is xy. So this part I leave it to you to check. So one can prove that, so this psi, it is a quasi-isometry and distance between this X and psi compose phi X. So this is less than equals to K square plus epsilon K. So the bound depends only on this K and epsilon, and distance between Y and phi compose psi Y is again a less than equals to F, some function of this K epsilon. So therefore, so we'll call this psi to be quasi-isometric inverse of this phi. . So check that this phi is also a quasi-isometry. So this psi will be called to be quasi-isometric inverse of this phi. Okay, so now let us take a triangle in Y. So we want to prove that Y is a delta prime hyperbolic metric space. So we need to find that delta prime. So we start with a geodesic triangle in Y. So PQR, it is a geodesic triangle in Y. And so now what we have this map psi from this Y to X. So psi, it is a map from this Y to X. Psi is a quasi-isometry, and psi will take this geodesic joining this PQ to a quasi-geodesic in X. So each side of this triangle, it will go to a quasi-geodesic. So in X, you will get a quasi-geodesic triangle, psi P, psi Q, psi R. And because of the earlier proposition, you can take the quasi-geodesic to be continuous. And now what you do, you take the geodesic triangle psi P, psi Q, psi R in X. Yeah, psi is a quasi-isometry. So psi of PQ, psi of QR, psi of RP, so are quasi-geodesics in X, and they form a quasi-geodesic triangle. Now consider the geodesic triangle psi P, psi Q, psi R in X. Now because of the stability of quasi-geodesics, so the geodesic joining psi P and psi Q will lie in a R neighborhood of this psi of PQ. That follows from the stability property. So each side of the triangle, so this triangle, so each side, so this will be contained in the R neighborhood of the quasi-geodesic sides of that quasi-geodesic triangle. So that is the thing it is written here. Now as X is delta hyperbolic, so this triangle PQR is, sorry, so here this X is delta hyperbolic metric space. So psi P, psi Q, psi R. So this will be delta slim triangle. So this will also imply that the quasi-geodesic triangle will be delta plus 2R slim. So as psi is quasi-isometry, so there will exist some delta prime greater than equals to 0, such that so this triangle PQR is delta prime slim. So what we have proved that this quasi-geodesic triangle, so this red triangle here, so this is a quasi-geodesic triangle, so this is delta plus 2R slim, and because this side is a quasi-isometry, so therefore this triangle PQR, so this will be delta prime slim. So this delta prime depends only on this delta K and epsilon. So I leave this as an exercise to check the details. Okay, so I'll stop here.